Hi friends, my name is Yashwant. I am from CSC department from Johnson Institute of Technology first year. Today my topic is about application of numerical methods in weather prediction. First, numerical weather prediction. Numerical weather prediction uses mathematical models of atmosphere and oceans to predict the weather based on current weather condition. Through first atmosphere in the 1920s, it was not until the advent of computer simulation in 1950s that numerical weather prediction produce realistic results. A number of global and regional forecast models are run in different countries worldwide using current weather absorption relayed from radio zones, weather satellites, and other observed systems as input. Next, mathematical model based on same physical principles can be used to generate either short-term weather forecast or long-term climate prediction. The latter are widely applied for understanding the projecting climate change. The improvements made to regional models have allowed for significant improvements in tropical cyclone track and air quality forecast. Manipulating the vast data sets and performing the complex calculation necessary to modern numerical weather prediction require some of the most powerful supercomputers in the world. More fundamental problems lies in the chaotic nature of the partial differential equation that govern the atmosphere. It is impossible to solve these equations exactly, and small errors grow with the time, doubling about every 5 days. Presenting understanding is that chaotic behavior limits accurate forecast to about 14 days, even with accurate input data and a flawless model. In addition, the partial differential equation used in the model needed to supplemented with the parameterization for solar radiation, moist process, cloud and precipitation, heat exchange, soil vegetation, surface water, and the effects of terrain. Next, computation. Numerical computation methods have found widespread use in nuclear magnetic resonance spectroscopy. Being able to simulate nuclear spin interaction is not only important for interpreting NMR spectra in the terms of molecular constituent structure, dynamic, and interaction, but is also important in the development of new experimental methods, for example, in terms of designing powerful new pulse sequence. This has fostered the development of vast number of homemade locally used programs as well as advanced software packages including widespread programs such as Gamma, Simpson, Spin Evolution, and Spinach. This also applies to magnetic resonance imaging, being inherently linked theoretically to NMR and to fields in many respects same frequency and pulse sequence design. This article describes pulse sequence design frameworks from an algorithm viewpoint supplemented in the last section by a series of examples and addressing the contemporary applications of algorithm in liquid and solid state NMR and MRI. Next, parameterization. Parameterization in a weather or climate model in the context of numerical weather prediction is the method of replacing processes that are too small scale or complex to be physically represented in the model by a simplified process. This can be contrasted with the other processes. Example, large scale flow of atmosphere that are elliptically resolved within the models. Associated with this parameterization are various parameters used in the simplified process. Example include the descent rate of raindrops, convective clouds, simplification of atmosphere, radiative transfer on the basis of atmospheric radiative transfer code, and cloud microphysics. Radiative parametrization are important to both atmospheric and ocean modeling alike. Atmospheric emissions from different sources within individual grid from boxes also needed to parameterize to determine their impact on air quality. Next, domains weather and climate forecasting, agriculture crop simulation, business forecasting, including demand, supply, and price forecasting, macroeconomic forecasting, political geopolitical forecasting. This includes forecasting election results, public opinion on issues, armed conflicts or political violence, and legislative changes, demographic forecasting, including forecasting of population, age structure, birth, death, and migration flow, energy use forecasting, demand forecasting, price forecasting, and supply forecasting, including forecasting of conventional and alternative energy sources, borrows some general ideas for business forecasting, technology forecasting. Next, ocean surface modeling. One of the important applications of satellite surface wind observation is increased to accuracy of weather analysis and forecast. The first satellite to measure surface over the sea set in 1978. On board was a scatterometer which measured radar backscatter from centimeter scale capillary waves from which surface wind speed and direction could be deduced. In more recent years, passive microwave remote sensing of ocean surface has provided extensive observations of surface wind speed, and advanced scatterometers have been providing surface wind velocity data over the ocean. The initial impact of satellite the surface with wind data and weather analysis forecasting was very small, but extensive research has been conducted since the early days of CSAT to improve the data accuracies and the utilization of this data in atmospheric model. Current satellite surveys and wind data are used to improve the detection of intense storms over the oceans as well as improve the overall representation of the wind field in numerical weather products. These are the two diagrams for ocean. Next, wildfire modeling. The weather plays a significant role in how wildfire grows, how fast it spread, and how dangerous it can be become for firefighters. But few tools exist to help fire managers anticipate days when weather conditions will have the greatest potential to make wildfire erratic or especially dangerous. The USDA Forest Service is expanding the options with the Hot Drive Index HDW. HDW, a new fire weather prediction tool based on the key atmospheric variables that affect wildland fire, temperature, moisture, and wind. Next, air quality modeling. The importance of interest to research and investigation of atmospheric compression and its modeling for different applications are substantially increased. Air quality forecast (AQF) and assessment systems help decision to makers improve air quality and public health, mitigate the occurrence of acute air pollution episodes, particularly in urban areas, and reduce the associated impact on agriculture, ecosystem, and climate. Advanced resolution emission inventory, satellite observation, and surface measurements of most relevant chemicals. Thank you.